So we've looked at periodic motion of simple systems, and we know how to analyze that motion, and we came up with some interesting relationships for some specific types of systems. In particular, we're looking for systems that exhibit simple harmonic motion. And what that means is we have uniform circular motion that we could break up into its x component or its y component. And we found that a system called a mass spring oscillator matches it perfectly. And we went through the free body diagram for this system and found that it created a second order differential equations, which then, when we integrated, we found that it turned into a sinusoidal function that matches uniform circular motion. And we call that type of system simple harmonic motion. So let's try out a sample advanced placement free response question of this type. So this is from the 2012 AP Physics C Mechanics exam. This is question number 1. And I need to caution you, when you're doing these questions, it pays to take your time to read the questions and circle some key ideas. So I'll give you a moment to read this. You can pause. For this first part, they ask you to come up with the equation for this sinusoidal function. And to tell you the truth, you don't need any physics to do this. They tell you what they want to call the function is velocity is a function of time. We've got a time axis here, we've got the velocity axis here, we've got data to pick up. And how do we map out this function? Certainly, it looks like a sinusoidal function, and we know from our study of this topic that it should be. So let's just use our math skills to answer this, rather than going through some more technical route using physics. I think it's much faster and it's straight to the point. So what type of function is this? Well, sinusoidal function, it's starting at 0, so that indicates that it could be a sine function. And rather than going up like a normal sine function is, it's going down, so I'd imagine that it's a negative sine function. And so what we're going to do to model this is we're going to use a negative sine function. All we have to do now is plug in the amplitude and the angular frequency. So to find the amplitude, easy, just pick it up off your graph, and you'll have to estimate where it is. I'd use certainly the closer value rather than a further one, and I estimate it as 0.16 meters per second. Be careful with your units. And then for our angular frequency, well, we know that relates to the period of the function, and the period of our function is, if you go from the 0 point to the next 0 point in the corresponding position, it's 0.7 seconds. And of course, we know that we can use omega equals 2 pi f and f equals 1 over t to come up with our angular frequency. And when you plug in numbers, you find out that's 8.89 radians per second. Once again, be careful with units. Plug those into your relationship, and there's your answer. Easy. You could double check if you'd like to by plugging in some values for t. For example, 0 seconds should come out to be 0, 0.7 seconds should come out to be 0, 0.35 should come out to be 0. But more interesting, I'd go halfway in between to get the high points and low points. They tell you that your equilibrium position is at the x equals 0 position, and then they ask you to find the equation x of t for the same data that they were given. So from the last part, we already know what the velocity function is. So what we need to do is, well, how do we find a position function given a velocity function? Go back to September at the beginning of the course. Well, we integrate. Take the area under the curve, we integrate. So I'm going to find our velocity function by integrating v of t dt plus our constant of integration. I'll tell you how to handle that later. Go ahead and do this, and when we do this, our constant negative 0.16 meters per second can pop out front. And then you ask yourself, if you look at it from an antiderivative perspective, the derivative of what function gives us a sine function? Well, it's a cosine. In fact, when we do cosine to sine, it's a negative, so we're going to have to throw a negative in as well. And because we have an 8.98 t in here rather than plain old t, we're going to have to multiply also by a factor to knock that out, so a 1 over 8.98. And so this is what we do when we do the antiderivative. And the question is, what do we do with a c? Well, the c is basically our equilibrium position. If our equilibrium position was offset by 10 centimeters, for example, our c would have to be shifted by 0.1 centimeter. This is an upward down shift on our x versus t graph, motion graph. Plug in our numbers, that's our answer. Should have circled that. Double check your answer by going back to the diagram, making sure things make sense. So we should have our min and max positions that match up with this function, and our amplitude should be 0.0179 meters, which is 1.79 centimeters. It's a very small spring with a small mass. And go ahead and try plugging some numbers in and see if they match. So there is an alternative way to tackle this problem. And so what you can do is start at the same point. You know your velocity function, and they told you the equilibrium spot was 0. And so then I would look at the general form that you know that a spring mass system has for its position and velocity functions. For its position functions, it's operating the x direction, and it starts in the plus side of the x-axis. So we'd use a cosine function to model that. The amplitude would be the same, would be an amplitude we have to work out here. And our angular frequency should be the same as we have up here. So we already know part of this. And if we take the derivative of this, we have the derivative of cosine is a negative sign, and our a just carries out front, and we have to do the chain rule, and the derivative of omega t is omega, that pops out front. So if we compare these two equations, you'll notice our omega is 8.98, as I mentioned, and the negative 0.16 must be equivalent to this negative AW. So those two things I'm going to set equal to each other, and then I'll solve for A. And so I'll go ahead and plug in. I'm just showing my units just so I make sure units are consistent here. Solve for A, and I get 0.0178 meters, just as I did on the other methodology. So there's our answer, and once again you should do a sanity check as I showed you on the last page. For part C, they ask you to calculate the value of K. So what do you know about a spring mass oscillator that includes the value of K? What relationships? Well, they give you on your formula sheet, if you don't remember it, one of these two things. I think it's the period they give you. And you can use that because you know several things in this already. So I would take your period, solve for K first, and then go ahead and plug in the numbers you know. You know what the mass is. You know what the period is, so solve for K. And you get 24.2 kilograms per second squared. The question is, are those the correct value for K? I thought K was in newtons per meter. You should double check and verify that these units are the same, and I would state my final answer in the more traditional newtons per meter values. For part D, once again, make sure that you read the question carefully. So what I'm going to do is I'm going to highlight a couple items in here that are interesting. First of all, it's on a rough surface. That means we have to involve friction here. Now, if you read the question, they tell you that the spring is compressed at a distance of d over 2. That means, well, if this is the equilibrium point, on the right side of it here, we're stretching the spring. On the left side, we're compressing. And if the block at the point in time where they're trying to find a free body diagram for is at d over 2, it must be sitting right in here on the compression side. So there's our mass. I just represent it as a dot like we have down here. And then they ask you to label the forces. Don't use components. Make sure you're following their instructions that act on the block when it's moving in the direction indicated below each dot. Well, in the first case, they're at this dot, and they want you to be moving towards the equilibrium position. So we're moving to the right. So we've got a velocity to the right. If you think about it, the spring is starting to uncompress, and the object is speeding up as it moves towards the equilibrium position. So what forces do we have in this situation? Well, I always like to start with gravity. And of course, if we have gravity pulling the block down, we've got to support it with a normal force, and those will be equal opposite, because this is in equilibrium in the y direction, static equilibrium. In the other direction, the spring is compressed still, so the spring is pushing us to the right, so we have a pushing force to the right. And because we do have friction, the friction is counteracting our motion to the right, so the friction has to be acting to the left. Now, it asks us what happens when we're at the same exact point, but we're moving away from the equilibrium positions. That means we're going to be moving to the left now. So our velocity is moving to the left. That means we are in the process of compressing the spring, which means we must be slowing down. So once again, we've got gravity, we've got a normal force. The spring is still pushing us to the right, so there's no difference with a spring force. The only force that really changes here is the frictional force, because now we're moving to the left, which means our frictional force must be opposing that and moving to the right. So once again, this is a tricky question if you don't read it carefully and take some time to read. As you recall, this spring mass system is moving back and forth, but now there's friction. So how does that affect our situation? It tells us here that we're going to assume that there's a negligible change in the period of the function. All right, that's very helpful. And they ask us to sketch out a velocity versus time graph. So we're going to draw a sketch, so we don't need a huge amount of detail, so they're not looking for tons and tons of numbers here, but there are some key numbers we can include. And this is a key idea, that the period doesn't change. And if you think about it, when you're on a swing set swinging back and forth, there's always going to be some resistance. In fact, when you did your pendulum experiment, same type of situation. That's simple harmonic motion as long as you have a small angle. The pendulum, regardless if it was moving fast or if it was slowing down, it always actually still moved at the same period, roughly speaking. And you would see this on a set of swing sets if you had a bunch of kids swinging on a swing sets all the same length. There's some frictional resistance up in the hinge that's pulling back and forth. Over time, those kids will slow down. Or if you could take the opposite effect, rather than bleeding away energy, you could be pushing somebody and adding energy to the system. And even in that case, the period would be the same. It's just that their amplitude would be increasing now for their velocity. So what's going to happen here is, because we know there's a negligible change in a period, we can actually sort of sketch out where the periods will be. And we know that because this is starting in the compressed position on the left side of the block, it's going to be uncompressing and moving to the right. So our velocity will start at 0 because we haven't let it go yet. Once we let it go, it'll be moving to the right, so the velocity will be increasing. And we know that since our period stays the same, we'll have zeros everywhere we have a full period. So we'll plot those first. And then, as I mentioned, because we have this bleeding off energy because of the friction, rather than having a constant sinusoidal function as we saw in part A, the amplitudes of each one of those peaks will slowly decrease over time. And so we'll get something like this. And that's actually called damping. We're damping the oscillations. And we can draw an envelope function around it. And if you look down here, and if you read your chapter, they'll give you some background on this. But basically, you have some sort of exponential decay function or some other type of damping function that will actually bleed off. Well, you can actually calculate that, and you can see how the energy is bled off. This e to the minus bt comes from the resistive force section, chapter 6.4, and that's where they picked that up from. And they brought the two concepts together. Just a little bit about damped oscillations, and these slides are from the publisher of our book. And so in real systems, we do have friction. We know that. And so as you were running your pendulum back and forth, you saw it slowly losing its energy. And so when this happens, the total energy, if you don't include the non-conservative work done by friction, the total energy of the system decreases. And if it decreases, that means the velocity has to decrease over time. We're damping that sinusoidal waveform. And it looks something like this. And this actually is pretty important in terms of your car, because your car is on a set of springs. And if you didn't have damped springs, you'd be driving along the road. Every time you hit a big pothole, you'd just go bouncing around on the road and never damp those springs on your car. And what's damping those springs is your shock absorbers. Your shock absorbers are filled with fluid, and as you try to push a piston through that fluid, it slows down your car quite rapidly. So it'll allow you to bounce initially, but then it'll damp those oscillations very quickly so you don't bounce off the road. You'll know when it's time to change your shock absorbers when you don't damp the oscillations, and when you hit a big bump, you'll just keep on bouncing and you'll bounce yourself off the road, which is a very serious situation. So if your car is too bouncy, you can try it out by putting your foot in your car and giving your back end a big push and your front end a big push. See if it settles out quickly or if it keeps on bouncing. There are other types of damping as well. If you overdamp something, it won't bounce at all. You'll never get to your equilibrium point. If we critically damp an oscillator, we'll damp it so much we never even get back to our equilibrium position. And if we overdamp an oscillator, we end up with a similar situation. And typically what we're looking at is this type of situation. I just want to remind you that a simple pendulum has the same mathematics, the same physics as the spring mass oscillator, as long as your angle is small. And what we do is a small angle approximation where we let sine of theta equal theta. And we use an arc angle here where it turns out that your distance you travel to the right, which is your x value, is approximately equal to your arc length in that case. And then it turns out to be the exact same mathematics as a spring mass oscillator. And so they give you the period for this is t equals 2 pi squared of L over G, and you can do the same mathematics.